Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks, section 10.2, titled The Bijection Rule. In fact, this section goes over a couple rules, a bijection rule and a k to 1 rule for counting. Hopefully you remember what a bijection is as well. They'll go into it. Alright, so you see some sets are easier to count than others. One way to approach a difficult counting problem is to show that the cardinality of the set to be counted is equal to the cardinality of a set that is easy to count. The bijection rule says that if there is a bijection from one set to another, then the two sets have the same cardinality. Now remember what a bijection was, hopefully from an earlier chapter on functions. A bijection was a function that was both one-to-one and onto. Right, so that means no two inputs went to the same output, that one-to-one, and onto meant every value in the target was in the range, right? Every value in the target was hit. So remember, a function f from a set S to a set T is called a bijection if and only if f has a well-defined inverse. And the inverse of a function f that maps set S to set T is a function g that maps T to S, right? It just reverses the mapping, is all this says, right? So here's the bijection rule. Right? If S and T are finite, if there is a bijection from S to T, if you can find one, then the cardinality of S must be equal to the cardinality of T. Alright, so their first example, a pretty simple one. Suppose that every person in a theater must submit a ticket to an usher in order to enter. So one way to count the number of people in the theater is to count the number of tickets submitted. In this case, the bijection is from the set of submitted tickets to the set of people in the theater. Right. Because again, they're one-to-one. Two different tickets aren't going to the same person. And it's onto because every person in the theater has a ticket that they submitted. So each ticket is mapped to the person who submits the ticket to the usher, right? The inverse function would map the person to his or her ticket. Number of people equals number of tickets. Right? Pretty simple bijection example. This next example uses the bijection rule to determine the cardinality of the power set of a finite set X. Now remember, the power set is the set of all subsets of X. So suppose the cardinality of X is N. The animation below illustrates a bijection from F, or a bijection F from the power set of X to the set of binary strings of length N. So you see X here has a length of 3, or a cardinality of 3. And really, you can think of the binary strings here. Every time there's a 0, that means an element is not in the set. And every time there's a 1 in a position, that means an element is in the set. So like 0, 0, 0 means that none of the elements are in the set. That's the empty set. And the empty set is a subset of all sets. 1, 0, 0 would be like A is in the set, but B and C are not. So you see set with A. 0, 1, 0 for B, the set with B. 0, 0, 1 for the set with C. 1, 1, 0 for the set with A and B. 1, 0, 1 for the set with A and C. 0, 1, 1 for the set with B and C. And 1, 1, 1 for the set with all three of them. Right? The whole set itself is a subset. Right? So the cardinality of this set is 2 to the third, which would mean that's the cardinality of the power set, 2 to the third. Now we saw this before, right? Remember the cardinality of a set, or the cardinality of the power set of a set was 2 raised to that cardinality of the set. We saw that before, right? But they're showing a bijection here between a power set and a set that's easier to count, right? The set of binary strings of the length cardinality of x. All right, blah, blah, blah. You can read all that. All right, so here, doing something similar to what was done in this activity. Again, you can watch the animation. I'm not going to play the animation. So here, for instance, suppose x is the set 1, 2, 3, 4. Define the function f from the power set of x to the set of binary strings of length 4, as defined above, right? Like I said, if there's a 0, it means the element's not in the set. If there's a 1, it means the element's in the set. So like, for instance, what's f of the set 1, 4? So that means 1's in the set, 4 is not. 4 is in the set, but 2 and 3 are not. So 1, 2, and 3 are not. So 0, 0, and then 4 is 1. Right. Which element is not in f inverse? Now this is going back. It takes a bit string of length 4 to some subset of x, right? To some set from the power set, from element of the power set. So it looks like 1, 2, and 4, but not 3. Right. How many elements are in the set f inverse? None, because it's the empty set, right? This would correspond to the empty set. Right. So again, simple bijections, a couple simple bijection examples. If you have a bijection, right, a one-to-one and onto function between two sets, those sets have the same size, the same cardinality. All right. So next, we've seen one-to-one functions. We're going to talk about k-to-1 correspondences, or k-to-1 functions. So the k-to-1 rule. This just means that every element in the target is mapped to by exactly k elements in the domain. All right, I'll explain all that down here. You can read the example. Here's a k-to-1 correspondence. So let x and y be finite sets. The function, from f from x to y is a k-to-1 correspondence if for every y and y, right, so for every element of the target, there are exactly k different elements in the domain that map to it. And if that's the case, that means the cardinality of x is k times the cardinality of y. Or you could say the cardinality of y is the cardinality of x divided by k, and that's what's being said down here. So suppose there is a k-to-1 correspondence from a finite set A to a finite set B. That would mean that the cardinality of A is k times the cardinality of B, or the cardinality of B is the cardinality of A divided by k. Same thing. So look at this example. Now I'll play this animation here. So you see how there are 6 cans of juice per pack. So if f of c equals p, if can c belongs to pack p, then this function f that's being described here is a 6-to-1 function, right? Because for every pack number, there are 6 cans that map to that pack number for every single one. So that would mean the number of cans is 6 times the number of packs, or the number of packs is the number of cans divided by 6. Right. So the number of cans, again, divided by 6 is the number of packs. Very, very simple example of a k-to-1, or in this case, a 6-to-1 correspondence. All right. So here's another example. This is a short section. We'll get more into this, the use of this bijection rule and k-to-1 rule later when we talk about permutations and combinations. These rules will come back and be nice and come in handy in those scenarios. This is just a nice short introduction. So a farm orders, X horseshoes for its horses. The farm does not order extras, right? And all the horses will get new horseshoes. And I'm supposing we're also assuming that all the horses still have all four of their legs. Apply the k to 1 rule to determine the number of horses on the farm. Express your answer as a function of x. It says you should not need the ceiling or floor functions. All right, I'll bring up a piece of paper here. If we're doing a horseshoes to horses function, here's a horseshoes to horses. All right, let's say I got 8 horseshoes here, and then 1 horse. I'll make it a little bigger so you know it's a horse. That's not a drawing of a horse or anything, but remember, every horse will have 4 horseshoes that go to it. And then this horse will have 4 horseshoes that go to it. And then so on and so forth. This would be a 4 to 1 correspondence, or a 4 to 1 function. Right? And if that's the case, the number of horseshoes, right, the size of the horseshoe set should be 4 times the number of horses. Now, this number of horseshoes they said they ordered was X. Right? They ordered X horseshoes equals 4 times, and I'll just say the cardinality of H for horses. So the number of horses then, the cardinality of this H set would be X divided by 4, right? Very simple. X divided by 4. The number of horseshoes divided by 4 would give me the number of horses on the farm. Again, if they didn't order extras, and if all the horses still had all 4 feet and needed to be shoed, it would be X divided by 4. So again, that's another simple example. Right? This whole section is kind of just a simple introduction to the bijection rule and this k to 1 rule, which will be used in greater capacity, which will be expounded upon in future sections. Right? But hopefully you understand the concept of the rules right now. And then you have your additional exercises. Again, some of these might be on your assignment, some might not. I would still recommend looking at all of them. Get more practice, more exposure to the material. You also have the solutions you can look at if you wish, but please try to work through them. Try to work them out on your own first before you go looking at the solutions. Just use the solutions to check your work, because if you're just copying down the solutions, you're not going to learn anything. And of course, if you have any questions, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.